as the SP is watching TV, the SP and TV. So for internal energy, the natural variables are S and V, that is entropy and volume. And for enthalpy, we have S and P, that is entropy and pressure. For Helmholtz free energy, we have T and P. For Gibson free energy, we have T and P. Okay, so natural variables are variables that are held constants in every thermodynamic process. If you all remember that, that's what we were taught. And what? And another definition is thermodynamic potentials. We say that these are set functions that, together with corresponding equations of state, describe the equilibrium behavior of a system as a function. Which the function are so-called the natural variables. That is what I have. Thank you.
Okay, now that you have mentioned about thermodynamic changes, maybe just as an example you have asked, usually you also check on what is the importance of the thermodynamic potentials. So you can study to get that. That's in your bank, data bank. So the next person.
The next question.
Do you want you have something to present, or you want to talk?
I have something to present, but I don't have the slides.
Okay.
So what Peter Mutika and Adams have presented, it's part of it is one of the part of what to present. So I will go through this, some things more than I add something on what they have presented. So my topic was about the thermodynamic potentials and thermodynamic characters. And on that, I looked about the internal energy, which we said that the natural variable are SP. And also there's an equation that represents the internal energy, that is denoted by U is equals to D ds minus PdV. So that equation represents the internal energy. Also, I also looked about the enthalpy. There is also an equation there which is dH is equals to dds plus VdP, and the internal variable is SP. We also have the Gibbs force energy, which is represented by the equation dG is equals to VdP minus SdT, and its natural variable is PT. And the last one is Helmholtz free energy, which is denoted by dF is equals to D.
Hello? Did we lose Peter or the connection on my side?
It seems like we lost him.
Okay, maybe we can move to the next presenter, because he was talking about what we discussed.
Next presenter is Simon Cyrus.
Simon of Cyrus. You want the right?
Good morning, members. No, I just need to talk. Good morning, Cyrus. Simon of Cyrus.
Cyrus is afternoon, not morning.
Sorry. Forgive me.
It is evening, Mr. Cyrus.
Okay.
It is afternoon.
Two systems. We have an open system and a closed system. An open system is a system that can exchange both matter and energy with its surroundings. An open system is a system that can exchange matter and energy with its surroundings. A closed system, the second type of a system, a closed system is a system that can exchange energy with its surroundings, but it cannot exchange matter due to the presence of a boundary. So the difference between an open and a closed system is that a closed system has a boundary that prevents the exchange of matter. As we talk about systems, we also have an isolated system. An isolated system is a system that can exchange neither matter nor energy with its surroundings. An isolated system can exchange neither matter nor energy with its surroundings. Moving from there, we have the state properties. A system can be described with its properties, and now we call them state properties. These properties include temperature, pressure, volume, density, viscosity, to mention just a few. So I repeat, the state properties include temperature, pressure, volume, density, and viscosity. As we talk about state properties, there we have two types of properties. We have extensive properties and intensive properties. When we talk about extensive properties, these are properties that depend on the amount of matter in a sample. So for a property to be extensive, it has to do with the amount of matter in a sample or in a system. So extensive properties include volume, mass, size, weight, and length. Just to mention that. When you talk about intensive properties, these are property of matter that depends only on the type of matter, and not on the amount of that matter. Again, I repeat, it's a property that an intensive property is a property of matter that depends only on the type of matter and not on the amount of that matter. So that this includes color, temperature. We have a very important situation, but just a few. To conclude, let me finish with the state function and path functions. A state function, also called a point function, is a property whose value doesn't depend on the path taken to reach that specific value. A state function or a point function is a property whose value doesn't depend on the path taken to reach that specific value. And this, we see it in functions such as internal energy, enthalpy, entropy, temperature, pressure, volume, mass, Gibbs free energy. So those are state functions. And lastly, we have the path functions. A path function is a thermodynamic property that depends on the path between the initial and the final state. Once again, I say that path functions or a path function is a thermodynamic property that depends on the path between the initial and the final state. This includes work. We know that work has direction, so the path taken is crucial. We have heat, we have loss of energy, probably due to friction, and all that. So that becomes about systems and their surroundings. We're talking about an open system, a closed system, an isolated system, And then we have talked about state properties, that is extensive properties and intensive properties. We have also talked about state functions, which are also called point functions, and path functions. Asante.
Thank you for that short and clear explanation. So far we have questions.
It's like consider U equals to this is that relation that we discussed in class. JK, you want to explain this slide? Okay, so I think so far David was trying to give us these relations in thermodynamic potentials. There are many of them. All these relations that we have here when it is in exact differentials. So writing all these things in differential form is what David was trying to explain. We have something here. Legendary transformation. This is a kind of special type of coordinate transformation. I don't know if anyone have something to say about the transformation in this slide, because the owner is not present.
I think this looks like the similar notes we have on the board already. The legendary transforms just basically he's trying to derive, he's trying to show how we can use the mathematical aspects to derive the Maxwell differentials. But I think we have seen this, which is simpler or easier. Doesn't mean presented this well, because so far thermodynamic potentials have been discussed and the Maxwell differentials have also been discussed. I don't think then the equations are kind of distorted. Some of them are not very clear. I don't know, on my side.
It means the zeroth law of thermodynamics, and basically the zeroth law of thermodynamics portrays temperature. So the first statement says that the zeroth law states that two thermodynamic systems in the same environment are in thermal equilibrium with each other. So it's a simple statement. If system A and C are in thermal equilibrium with system B, then A and C are in thermal equilibrium. Okay, I guess in the next slide. Okay, temperature and zeroth law of thermodynamics. Okay, there's a definition there. Heat, which is the transfer of energy due to temperature differences from hot objects to cold objects, and objects do not have heat. Heat flows due to thermal contact. So there must be a contact between two objects for heat to flow. May it be air or any other contact. Energy is transferred until the temperatures are the same. They are in thermal equilibrium. So basically thermal equilibrium is a region of same temperatures. Next slide. So just a replica of the same. It states that if system A is in thermal equilibrium with B and B is in thermal equilibrium with